All right, buckle up, everybody, because today we're diving deep into the world of reinforcement learning.
That's right.
We're going to be exploring
Yeah.
a research paper called Introduction to Reinforcement Learning.
Mm-hmm.
Now, I know research papers can be a little bit intimidating,
Yeah.
but don't worry. We're here to break it down
Right.
and extract the juicy bits so that you can understand it,
Yeah.
even if you don't have a computer science degree.
Absolutely.
Okay, so imagine this.
Yeah.
You have a computer program that learns to play chess,
Okay.
not by being programmed with all the rules and strategies, but by actually playing,
Ah.
winning some, losing some, and learning from its experiences.
Right.
That's the power of reinforcement learning.
That's really the heart of it.
It's like learning to ride a bike.
Yeah.
You don't just study the physics of balance
Yeah.
and then hop on and ride perfectly.
Yeah.
You wobble, you fall, you get back up,
Exactly.
and you learn from those mistakes.
And you get better over time. That's what's so fascinating about this approach.
Yeah.
It really does mirror how we humans learn in so many aspects of life.
Right.
We try things out, we make mistakes, and we get better.
Absolutely.
Now, the paper starts
Yeah?
by breaking down the fundamental building blocks of reinforcement learning.
Okay, so let's unpack those building blocks then.
Sure.
The first one I see here is state.
Right, the state.
Can you explain what a state is?
So a state is basically a snapshot of the environment at a particular moment in time.
Okay.
It's all of the information that the agent, our learning system, has
Mhm.
available to make decisions.
Okay.
So let's think about our chess analogy again.
Yeah, the chessboard.
The state of the chess game
Right.
would be the arrangement of all the pieces on the board at any given time.
Okay, so the state is like setting the scene, so to speak.
Exactly. It's the context
Okay.
in which the agent has to make decisions.
Okay, so then we have
Now,
actions.
Yeah, actions are what you can do in that particular scene.
Yeah, so what are those in our chess analogy?
So in chess, an action would be moving a specific piece
Okay.
to a specific square on the board.
Got it.
Of course, following the rules of chess.
Of course.
Of course.
You can, you know.
You can't just go wherever you want.
Yeah, move your pawn backwards.
Right,
It
exactly.
has to be a legal move.
Okay, so we've got the state,
Right.
we've got the actions.
Yep.
Now, how does the agent choose which action to take?
That's where policies come in.
Policies.
Yeah, think of a policy
Okay,
as the agent's strategy or decision-making rule book.
okay.
It takes the current state as input,
Right.
and then it outputs an action
Okay.
or a probability distribution.
Wait a minute. A
Okay.
probability distribution.
So it's not always going to make the same move
Oh.
in the same situation.
That's interesting.
So that's what we call a stochastic policy.
Okay.
Instead of being deterministic
Right.
and always doing the same thing,
Yeah.
it introduces a bit of randomness.
Yeah. It might say, in this state, I have a 70% chance of doing this,
Wow.
a 20% chance of doing that.
Okay.
And
So it's like almost like the computer's flipping
Yeah.
a coin,
Yeah, a weighted coin.
a weighted coin.
Yeah.
Okay.
I
That's cool.
To decide.
So why not just always choose what seems to be the best move?
Well, you don't want to get stuck in a rut, right?
Yeah.
You want to be able to explore and
Right.
try new things.
Makes sense.
And that's what stochastic policies allow you to do.
That makes sense.
You know, you don't want to just always exploit
Right.
what you already know.
Gotcha.
You want to explore new possibilities.
Okay, so we've got states, we've got actions, we've got policies.
Right.
How does the agent know
Yeah.
if its actions are any good?
Well, that's where rewards come in.
Rewards.
Yeah, rewards are the feedback mechanism.
Okay.
They tell the agent whether its actions are leading it toward its goal
I see.
or not.
Okay.
So it's like giving a dog a treat when it does a trick.
Gotcha.
Right.
Right.
So in our chess game,
Yeah.
a reward might be a positive value for capturing the opponent's queen
Oh, yeah.
and a negative value for losing your own rook, for example.
Gotcha.
So that reward function, which defines these values,
Yeah.
is something that's designed by us humans,
Okay.
the ones who are creating the reinforcement learning system.
Gotcha.
And it kind of encodes
Right.
the goals that we want the agent to achieve.
So that's how we tell it what's good and what's bad.
Exactly.
Okay, this is starting to feel like a game almost,
It is. It is.
which makes sense because we're talking about chess.
Absolutely.
You've got the state of the game, you've got your actions, your possible moves.
Yep. Yeah.
You've got the policy,
Right.
which is like your strategy.
Yep.
And then you've got the rewards that tell you whether you're doing well or not.
Yeah. Okay.
Yeah. Okay, so now we've got these core elements.
Right.
Building on those, the paper introduces the multi-armed bandit problem.
Yeah. This is a classic.
Okay, multi-armed bandits.
So imagine you're in a casino and
Yeah.
you're faced with multiple slot machines.
Right.
Each one has a different payout rate.
Okay, I like this analogy.
Those slot machines are bandits.
Okay.
And your goal is to figure out which one pays out the best.
Okay.
So you're going to try different machines,
Mm-hmm.
but you also want to keep playing the ones
Yeah.
that seem to be giving you good results.
Right.
This is the classic dilemma of exploration versus exploitation.
Okay.
You want to explore new options,
Right.
but you also want to exploit the ones that you know are working well.
Yeah, yeah.
And there are some interesting methods for
Yeah.
balancing that trade-off,
Oh, cool.
like the epsilon greedy strategy.
Epsilon greedy.
Yeah.
Yeah.
And the upper confidence bound algorithm.
Interesting.
So these algorithms,
Yeah.
they help the agent make intelligent decisions about when to explore and when
Okay.
to exploit.
Okay, so that makes sense.
Yeah.
It's like saying, okay, I've had some success with this slot machine, but let me try a few others.
Exactly.
Just to see if there's something even better out there.
Right.
Okay, so that's pretty cool.
Yeah, it's a really fundamental concept
Yep.
in reinforcement learning.
This is fascinating.
No, of course,
Yeah.
the multi-armed bandit problem is just a starting point.
Right.
Reinforcement learning can tackle much more complex scenarios.
Okay.
And that's where Markov decision processes come in.
Markov decision process.
Or MDPs, for short.
Okay, MDPs.
They provide a formal mathematical framework for
Good.
describing these more complex problems.
Right, so MDPs are kind of like the next level up then.
Exactly.
All right, well, I guess that's where we'll pick up next time.
Sounds good. Welcome back, everyone. I hope you're ready for more reinforcement learning fun, because we're about to tackle those Markov decision processes,
All right, MDPs.
or MDPs for short.
From what I understand, they're like the blueprints for more complex reinforcement learning solutions.
Exactly. They're the framework.
Okay.
They're tackling more sophisticated problems.
Can you remind me how they relate to those core concepts we discussed earlier?
Yeah, absolutely.
You know, the states, the actions, the rewards.
Right, so MDPs provide this formal mathematical framework
Oh,
for
yeah.
describing sequential decision-making.
Sequential decision-making.
Yeah, so where an agent interacts with the environment
Okay.
over a series of steps.
So instead of just looking at one decision point,
Yeah,
like choosing a slot machine,
exactly.
now we're looking at a series of decisions.
Yeah, it's like navigating a maze.
Okay, a maze.
Yeah, so the states would be the different locations in the maze.
Okay.
The actions would be the possible moves you can make, like north, south, east, west.
Okay.
And the rewards might be, positive for reaching the exit,
Yeah.
negative for bumping into a wall.
Okay, so the agent's goal is to find the exit.
Yeah.
Collect as many rewards as possible along the way.
Exactly.
Avoid those negative rewards, the walls.
Avoid those walls. But how does the agent know which path to take?
Right, that's where policies and value functions come in.
Okay, yeah, those were...
You remember, the policy is the agent's strategy.
Yeah, it's like the decision-making rulebook.
Exactly. It tells the agent what to do in each state.
Okay.
And the value function, that's all about estimating how good a state or an action is.
Right, so the policy is the doer.
Yeah.
And the value function is kind of like the evaluator.
Exactly. It's like the advisor.
Yeah, the advisor.
Whispering in the agent's ear, hey, this might be a good move.
Okay, so how do those two work together?
Well, imagine our maze agent starts with a really simple policy.
Okay.
Maybe it just moves randomly at first.
Okay, random.
Yeah, its value functions would be pretty inaccurate.
Because it doesn't know anything about the maze.
Right, it's just bumping around.
Bumping into walls.
But as it explores, it starts to learn,
Okay.
bumps into walls, maybe it finds some rewards.
So it's starting to build up a picture of the maze.
Exactly. And those value functions, they start to influence the policy.
Okay.
So instead of moving randomly, it starts to favor actions that lead to states that it now believes are better.
So it's like it's building a mental map.
Yeah.
Not just of the layout of the maze,
Right.
but also of where the good stuff is, where the bad stuff is.
Yeah, it's like a value landscape.
Okay, that's pretty cool.
And this process, it continues.
Yeah.
The policy and the value functions are constantly refining each other.
They work together
They work together.
to guide the agent towards better performance.
Exactly.
This is really fascinating.
It's like watching a child learn.
Yeah.
They explore, they play,
That's a good analogy.
and they figure things out.
So now we need to talk about the Bellman equation.
Right. This is a key concept
Okay.
that helps us formalize this idea.
Formalize the value of states.
Exactly. So the Bellman equation tells us that the value of a state
Yeah.
is connected to the values of the states that can be reached from it.
Okay, so the value of where you are now
Yeah.
is related to the value of where you could go next.
Exactly.
Okay.
Imagine you're at a particular location in our maze, right?
Okay, I'm in the maze.
The Bellman equation says the value of that location is equal to
Okay.
the immediate reward you might get there,
Okay.
plus a discounted estimate.
Discounted. What does that mean?
Yeah, so discounted basically means
Okay.
that rewards further in the future are worth a little bit less
Okay.
than immediate rewards.
Yeah, that makes sense.
Think about it. If I offered you $100 today or $100 a year from now.
I'd take the $100 today. A
Exactly.
bird in the hand, right?
Exactly. So we apply this discount factor,
Oh.
usually represented by the Greek letter gamma, to future rewards.
So it's kind of like taking into account the uncertainty of the future.
Exactly. You're prioritizing those
Okay.
immediate rewards.
Okay, so that's the Bellman equation.
That's the Bellman equation.
It connects the value of where you are
Yeah.
to the immediate reward you might get and the value of where you might go next.
And the discounted values of those future states.
Right, with that discount factor.
Exactly.
Okay, I think I'm starting to get it.
Good.
So are there different ways to learn these policies and value functions?
Yeah, absolutely. There are a bunch of different methods.
The paper mentioned model-free and model-based methods.
Right. Those are two big categories.
Can you explain those a bit more?
Sure. So model-based methods involve building a model of the environment.
Okay, so what does that mean exactly?
Basically, the agent tries to create a simulation.
Okay, like a little mini maze in its head.
Exactly. And this model allows the agent to plan ahead.
Oh.
It can simulate different actions and see what would happen.
Without actually having to try them out.
Right.
Okay, so that sounds pretty powerful.
It is powerful.
But I guess it can be pretty hard to build an accurate model.
Yeah, that's one of the downsides.
Especially for complex environments.
Right. It can be computationally expensive.
Okay, so what about model-free methods?
Those are more about learning from experience.
Learning by doing.
Exactly. They don't try to build a model.
Okay.
They just learn directly from the data.
So it's like exploring the maze without a map.
Yeah, you're just figuring it out as you go.
Okay, and that can be effective too.
Yeah, it can be surprisingly effective.
And it's probably simpler, right?
Usually much simpler.
Okay, so we've got model-based, model-free.
Right.
What about on-policy and off-policy learning?
Oh, yeah, that's another important distinction.
Okay, can you unpack those a little bit?
So on-policy learning is about learning from your own experiences.
Like learning to drive by driving your own car.
Exactly. You're only learning from your own actions.
Yeah.
Off-policy learning allows you to learn from other agents' experiences as well.
So like watching other people drive.
Yeah, and that can be a big advantage.
Okay, why is that?
Because you can learn much faster.
Makes sense.
You don't have to make all the mistakes yourself.
You can learn from other people's mistakes. Okay, I think I'm starting to see the big picture here.
Good.
We've got all these different categories
It's a whole taxonomy.
of reinforcement learning approaches.
Yeah.
So now, can we talk about some specific algorithms?
Yeah, let's dive into Q learning.
Q learning. All right, let's do it. All right, Q learning. This is a big one, right?
It is. It's one of the most well-known reinforcement learning algorithms.
So where does it fit into those categories we talked about? Model-based versus model-free, on-policy versus off-policy.
Right. So Q learning is model-free,
Okay.
and it's off-policy.
Off-policy, sorry.
So it learns directly from experience without building a model,
Okay.
and it can learn from data generated by a different policy.
So it's kind of like our maze runner.
Yeah,
Learning by doing, but also watching other maze runners.
exactly.
Okay.
So at its core, Q learning is all about learning this thing called the Q function,
The Q function.
or the action value function.
Okay, and what does that tell us again?
It tells us the expected long-term reward.
Yeah, right. The long-term reward.
Yeah, for taking a particular action in a particular state.
So it's like a guide telling the agent what to do.
Yeah, it's like a roadmap to success.
But how does Q learning figure out this Q function?
Right. So it starts with some initial guesses.
Okay, guesses.
Yeah, for the Q values.
Okay.
And then it updates them based on experience.
So it's learning, it's adapting.
Exactly. So imagine the agent takes an action.
Yeah.
It gets a reward.
Okay.
And then it sees the next state.
Okay.
And it uses all that information
Yeah.
to update its estimate of the Q value.
So it's like it's constantly refining.
Yeah, constantly tweaking.
Its understanding of how good different actions are.
Exactly, based on the feedback it gets.
Okay, that makes sense.
And there's this update rule
Okay.
that it uses to do this.
So it's like a formula.
Yeah, it takes into account the reward it got,
Right.
and the estimated value of the new state.
Okay.
It's a little bit mathematical.
We don't have to get into the math, right?
No, we don't have to get into the details.
Okay, good.
But the main idea is
Yeah.
that it's constantly updating its estimates
It's learned.
based on experience.
So what about these other versions of Q learning?
Right. So there are some interesting variations.
Like double Q learning?
Yeah, double Q learning.
And deep Q learning?
Deep Q learning. That's a big one.
Okay, what's double Q learning all about?
So double Q learning, it addresses this issue called maximization bias.
Maximization bias. Okay.
Yeah, it's a tendency for Q learning to overestimate values sometimes.
So it's like being overly optimistic.
Yeah, like thinking every move is a good move.
Okay, and double Q learning fixes that.
It uses two Q functions.
Two Q functions.
Yeah, like getting a second opinion
Okay,
to help reduce that bias.
interesting. And what about deep Q learning?
This is where we bring in deep neural networks.
Deep neural networks, those are the powerful ones.
Yeah, they can learn complex patterns,
Image recognition, natural language processing.
all sorts of things.
Okay, so how do they work with Q learning?
So in deep Q learning,
Yeah.
we use a neural network to approximate the Q function.
Okay.
And that allows us to tackle problems with huge state spaces.
So like a really complex maze.
Yeah, or a video game with millions of possibilities.
Right. It can handle that complexity.
Exactly.
This is awesome. It's like giving our agent a super brain.
It is. It's pretty remarkable.
Now, I know we talked about Q learning and its variants, but what about those policy-based methods?
You have policy-based methods.
They focus directly on the policy, right?
They do. They try to find the best actions directly.
Without worrying about the value functions.
Yeah, they skip that step.
Okay, and what's an example of a policy-based method?
One of the classic ones is called reinforce.
Reinforce.
Yeah.
How does that work?
It updates the policy based on the rewards it gets.
So if an action leads to a good reward,
Yeah.
it's more likely to do that action again.
Exactly. It reinforces good behavior.
Okay, that makes sense.
And it's been used in a lot of different applications,
Cool.
especially in robotics.
Robots learning from their experiences.
That's right.
Okay, and then finally we have actor-critic methods.
Yeah, actor-critic methods.
These are the hybrids, right?
They are. They combine value-based and policy-based ideas.
Okay, so who's the actor and who's the critic?
So the actor is responsible for choosing actions based on the policy,
Right.
and the critic evaluates those actions.
Okay, so they work together.
They do. It's like a feedback loop.
The critic's giving feedback to the actor.
Exactly, helping the actor improve.
This is amazing. We've covered so much.
We have. It's a whole world out there.
From the basics of reinforcement learning.
To some really powerful algorithms.
It's really mind-blowing.
It is, and this is just the beginning.
I know. It's crazy to think that
Yeah.
we can create machines that can learn and adapt like this.
It's really changing the world.
So what's the key takeaway for our listeners today?
I would say the biggest thing is that reinforcement learning is about creating agents that can learn from experience, solve problems,
Yeah.
and adapt to new situations.
It's really a glimpse into the future of AI.
It is. It's a really exciting field.
Well, thank you so much for taking us on this deep dive into reinforcement learning.
It's been my pleasure.
To our listeners, be sure to check out the show notes for more resources.
Yeah, there's lots of great stuff to explore.
Keep those minds curious and keep learning, and we'll see you next time.
See that?